at afterwards.
Yeah. Okay. So Kip's told you some of what are regarded as the facilities limits, and of course you've heard of all kinds of noise sources. I'm just going to use overhead projections here. And I'll have to go, there's a lot of ground I'd like to try and cover if there's time, if I can do it. So, I was looking last night to get some curve equivalent to that. What I did get was one that actually is a curve for, I think you've already seen, from Alan Weinstein in one of his talks, a curve for LIGO 1.
The gravity gradient noise when this graph is wrong, it's too low by considerable factor.
Anyway, don't worry about the details right now. This was for basically LIGO 1, and LIGO 2 is better. The reason I thought this is an interesting one is that it breaks down many of the noise components. And of course, what you're getting is a sum of all these noise components, plus a whole lot of practical problems. And let me start off right away by a kind of introductory view graph, pointing out that, first of all, the first thing you've got to do is make your interferometer work. And that, to work down to what you expect, the performance you're expecting, that's likely to be a really tough problem. That's not a theoretical problem, that's a practical problem. Because, for example, LIGO, all detectors built so far, none of them have got anywhere near their expected performance. So, but because there's dozens of practical problems. I had a lot of experience in this in making the first 40 meter, which was the first test interferometer, and we started off many orders away from the predicted performance, and roughly a group that I was working with, we roughly, at the best of times, we improved a factor of 10 per year, roughly, working hard for quite a lot of years. So that just shows you there's dozens of problems which you don't expect because no one's quite predicted them, and you've got to find them, isolate them, identify them, and fix them. And that's happening. Now, it'll not be so bad with LIGO because hopefully many of the problems LIGO is now seeing are ones that have been found before on smaller systems. But so you don't really expect to get to these theoretical, at least I don't expect anybody to get to the kind of theoretical limits we're talking about on the large interferometers for quite some time. Okay. So that's the main thing, make it work and to get to the fundamental limits. But even then, of course, what we know is that the kind of theoretical limits are not really quite good enough. So you've got to try and see how you're going to push the theoretical limits, how you're going to push past that, get better theoretical limits. And so that's really what I'm talking about here, assuming that you've beaten all the practical problems, which are immense and tend to be forgotten because most of them are kind of unpredictable. Okay, so, and you've already seen before the different ones, sensing, noise. Quick comments on some of these. First of all, sensing noise, where we all started off, basically when this whole kind of work started, the obvious thing was, how do you do it with light of wavelength, near a micron, and you're trying to measure 10 to the minus 10 times better than that. Okay, well, you've all seen how all that's done now. But then you still have the short noise. You will eventually get to the quantum limits, but already you've heard in earlier talks in this series how to beat that, theoretically. In fact, my view has been for a long time that the difficulty is not going to be to beat the quantum limit. The difficulty is going to be to get to the quantum limit, because there you've got to beat all the practical problems of the thermal noise. I think that's harder. Once you get to the quantum limit, I think we'll just sail through it by switching on the quantum non-demolition switch. and that will be easy in comparison. I mean, actually hard, really seriously hard too, but the others harder, I think, still. Okay, some of these graphs, for example, show, if we go back to this one, this was the one, I'll use this one because this was the one I was looking at how to comment on here. Some of these show noise sources which are fairly easily fixed. For example, this is short noise, this corresponds more to the quantum limit, but what's this radiation pressure noise here? Well, that's a kind of stupid one. That's really the radiation pressure of the light. But in fact, in this region here, this, I think, curve was made assuming that you kept the laser at the same power for all parts of the spectrum. And if you're serious here, you wouldn't do that. You would turn down the laser power, and this can usually bring this down. Now, of course, that's easier said than done, because on the LIGO scale, the power is so high that all the optics is being heated and therefore being deformed by the heat of the light. If you turn the power down, there's less heat, so all the mirrors are going to be deformed a different way, and they were all designed to operate at high power. So it's not as easy, but it clearly can be done. So,
you mean you're talking about turning the light power down?
Yeah.
When do you want to do studies?
yes, at low frequencies.
A day or two doing studies at low frequency.
Yeah, that's right. That's right. So, or you might build a second interferometer in the beam pipe or something that was specifically reserved for low frequencies. There's a lot of argument. I did a lot of early thinking about this. You might want to have several different interferometers for different parts of the spectrum working at the same time, maybe even in the same beam pipes. There's room for that. Okay, so that's not so serious. The real, and seismic noise, that seismic isolation, Kip just mentioned it, there's dozens, that's in a sense a kind of mundane source. It's a tough one practically. Theoretically, it's very easily fixed, theoretically. And practically, it's proved much harder than people kind of expected. But there's no doubt at all that that is fixable. And there's many ways to do it, and they're all a bit complicated, and if we had time, we could discuss them. So let's assume that's beaten. It's not easy, but it can be done, and I've been working on experiments testing various ways to do that. Okay. The real tough one is, in fact, the thermal noise. Where can I put these? Okay. Oh yes, this was Kip's, the one he just gave me, and you've seen it, facilities limits. Well, they're all the same kind of shape. This is presumably a better and more accurate one, although we'll see, as I said, I've got a funny puzzle. I've got a very recent Japanese one which shows about a factor of 10 difference. But anyway, let's not worry about that. Let's come back to that. I think we're lucky if the thing ends up anywhere near a factor of 10, as good as these numbers. Okay, thermal noise is really the tough one. Because what can you do? Well, first of all, suspension thermal noise, there are many ways you can see to improve that. We're using just fibers, quartz fibers, which is pretty good stuff for it, but you could think of all kinds of ways. For example, you can't make the fibers really thinner in cross-section because they're already highly stressed to near the breaking point, but you can flatten them so that they bend more easily in one direction, so use ribbons. You can push that further and further and further, and as it happens, the very first laser interferometer I built, which was a long time ago now, 1977 I think, or 1978 in Scotland, was a very weird one. It was the very first we ever made. It had quarter-ton test masses, only a few inches apart, with an optical system to measure distance between them. But that, as it happened, had what still seems to be the very best kind of suspension. It was a suspension, it was made on a big scale because we were hanging quarter-ton test masses, but there was actually blades of very high Q aluminum alloy that were 1 inch wide and only a few thousandths of an inch thick. And that's a very good idea. At the time, we had so many problems with everything else that we never knew if it was good or not. We found we did practically everything wrong about the optics, and it taught us a lot of things. And in fact, it led to the whole idea, led me to think of the idea of using fabric cavities, which was a kind of breakthrough. And that's what's used now in all. We were using a delay line, and if time we can talk about that. Okay, so anyway, but that's, so you can see easy ways to make the suspension noise better. Internal noise is a lot tougher. There's not much you can do there except getting higher Q material, and the stuff that's being considered now, sapphire and so on, is pretty well as good as you can get. So you may have to reduce, but you can see if you reduce the temperature, it would help that. You would help the internal thermal noise. Residual gases, you would certainly improve that. If you cooled the whole thing down to liquid helium temperature, the gas pressure would automatically get much, much less because the gas is going to be frozen out. The whole thing will be like a huge cryopump. So that's appealing, except that it's incredibly tough to do. And then stray light, well, there's all kind of tricks and so on. Particularly, there are, as well as me, the ones I don't know, Kip mentioned, there are clever optical tricks you could think of doing. Make the coherent length of the light short in some clever way. There's all kind of, so I'm sure that can be beaten. So let's talk about reducing the temperature. That's the obvious approach. Well, because it's obvious, even though it's obvious, it was only really taken quite seriously by the Japanese effort quite recently. People have thought about it for years, but always thought, gosh, these interferometers are too difficult to make already. Why make it 100 times harder by cooling it all? You've got enough problems. And that was a very sensible conclusion. But still, if you think ahead, yeah, it would be very good if you could reduce the temperature. And right now, the Japanese have been putting more effort into that than anybody else, and they have made really pretty firm plans for building a big cryogenic interferometer. And let me tell you something about that, because it's very interesting. Now, don't know when it'll happen, but I just found a description with a lot of details of it. And partly they're doing this because they've built a 300-meter interferometer quicker than anybody else has, and it's actually operating right now better than any other interferometer in the world. Here's a curve Kip you won't have seen. I only saw it yesterday. And this one's a factor of 10 different from you. This is a Japanese curve. This project, which is just plans, of course, in the early stages, but they're doing experiments too. And let me say a little bit, the background there is, chap leading this effort is Kuroda, who in fact has already done a cryogenic gravity wave experiment years ago, and it was a very successful experiment. It was an experiment to look for the gravitational waves predicted from the crab pulsar. So it was a mechanical device, a bit like a bar, but a kind of clover leaf pattern, pretty big, order of I think a ton or so, and all tuned up to the expected frequency of the crab pulsar. And it was worked. It was at liquid helium temperature. This was done in the Japanese KEK establishment, which is a big high energy accelerator facility that has lots of helium and so on. Okay, so this is their prediction. Now, first of all, let me first of all say cooling. So what do? You just say, okay, we just pour liquid helium all over everything. Well, you can't just do that. And the tough thing is that the important thing to cool is the test masses, but you can't touch them. And yet, because of course they're isolated, they're suspended on fibers and so on. And yet there's heat coming into them from your high-powered laser beam. Even though you get the lowest possible absorption in the material, there's even the very best materials, and people are working hard to get better, say quartz or sapphire. The absorption is typically a few parts per million per centimeter. And if you've got what might be half a megawatt or something, that becomes very serious input of heat. And how do you take it out? Well, you see, normal in cryogenic things, you have cryostats, and you can take it out by conductivity. You can't here. And the trouble is, well, the only connection is the suspended fibers, which are very thin. And so, and the radiation at low temperature is very small because it goes as T to the fourth. So in fact, when you can estimate, let's say, depending on just radiation, even though you had surrounded your test masses by shrouds at liquid helium temperature, or as low a temperature as you like, wouldn't make any difference. The equilibrium temperature is estimated to be around 10 or 20 degrees Kelvin, which is not very cold. So it's not so easy. And that's one of the things that's deterred people. Now, the current plans for this, they're doing lots of tests with test masses and so on, and in being cooled down and all that. And their plan is essentially what's a sensible, a straightforward plan to, in fact, suspend the sapphire test masses by sapphire fibers, maybe ribbons, I'm not sure which, it doesn't make much difference, and carry the heat through the sapphire. So the temperature will not be very low. I think they're estimating in the region again. Well, it's not very far, I think, from 10 degrees Kelvin. However, even 10 Kelvin helps you a lot. Sorry?
Why the LCD keep curving the high frequency fibers below LIGO 2 so you also higher power
The LIGO 2 curve is wrong. The minimum of the LIGO 2 curve is the same as what they've drawn for LCGT.
Yeah, I know, that's what I said. There was a factor of 10 roughly different here on the scale, so I don't know which is wrong.
They have LIGO 2 wrong. LIGO 1 is right.
Yeah.
LIGO 1 to LIGO 2 is a factor of 15.
Yeah.
And from the minimum to minimum. And that's about what they had from LIGO 1 to LCGT, it's factor 15.
I only got this curve, I should say, last night, so I haven't had time to work out what it is.
I think that may be incorrect curve.
What?
Also, that LCD curve may be incorrect.
Oh, so it should be lower too, should it? Because certainly it should be a lot better than LIGO 2.
Yeah, so they may.
So maybe there's other errors in scaling and so on. Thanks, you give me the curves. Thanks very much. Yes, you gave me the curve last night.
They recently corrected their curve.
Sorry?
So they recently corrected their curve. So they,
Oh, I see.
It may be old one.
Oh, okay. But thanks a lot. It was the first time I'd seen these curves.
Well, I would guess both those curves are lower than LIGO.
Yeah, look, it's quite likely that the scales are somehow there's something wrong in the scaling, but okay, but that shows the kind of idea anyway. Okay, and it's interesting to see these curves. You would certainly expect the low temperature one at about 10 Kelvin to be a lot better than LIGO 2. Now, okay, by the way, and one interesting little piece of practical, which I don't know if was really measured before, but they have already made some, they've been, as I said, been working for some years already on cryogenic tests of individual test masses. And here's a plot of the Q. Now you say, why does cooling help? Oh, I need something to hold that down. Anyway, it's not just that the temperature is lower because, of course, KT is less, but let's say you cut the temperature from 30 to 10, from 300 room temperature to 10 degrees Kelvin, let's say. That's a factor of 30. But the improvement only goes as, that's the power goes as KT, so the amplitude only goes as a square root of that. So you don't gain as much as you might well think. So in fact, it turns out that a much more significant effect than the plain reduction of the temperature and thus of the thermal noise is the fact that the Q of the materials you're going to use gets a lot better at low temperature. And that turns out to be a bigger factor than the temperature itself falling. And this is measurements in Japan of a kind of test mass showing the Q from room temperature here to, well, down to here to a few degrees Kelvin, right? 10 degrees, you're getting, it's a big factor difference. That's a bigger factor than you'd get just from the plain temperature. That's encouraging. And of course, it could well be that it's better than this, because if you have any other experimental problems causing losses, they would show up as they're not getting better. So it's going to be at least as good as that, and maybe better. That's encouraging, because that's a real measurement. Okay.
Those are violin mode measurements?
No. These are internal test mass measurements, I think. Not suspension.
It is.
Yeah. No.
And
so that's it.
and it's for sapphire?
Sapphire, yeah. It's interesting. I don't think anyone has done that before. No, they've got quite a big test rig at, well, it was all built at KEK, I think. This one is not in Tokyo, but you know where it is. Anyway, Kuroda's had a group working on this for quite a long time now, for some years. Okay, but these are the first measurements I'd seen. Okay, so that's kind of encouraging. Okay, so let's go on. Oops. Okay, now what else do we have here? Now, of course, another thing is, if you can reduce it, of course, the walls of it may not be necessary to cool the whole of the pipes. I think the Japanese designers put 3 kilometer vacuum pipes, and by the way, the plan is to put all of it pretty deep underground in rock. Sorry, something wrong?
It's only cooling 50 meters.
Oh, is that right? Okay, I wasn't quite sure. Okay, I hadn't read all the details there yet. Okay, anyway, no, okay, then they may just cool near the end. That's really all you need, and I'll show you later a design. I produced it with something like that, but just the end's cool. Now, okay, by the way, yes, they have a site chosen for this near the Kamioka project, which is a neutrino underground facility. It looks like that, seismically very quiet and good seismically, and people who couldn't walk near it because it's deep underground. Anyway, they'll put tunnels. I think there's one tunnel existing already. Okay, so where are we now? So zero gas, that'll automatically get better. Stray light's fixable in my view. Okay, so maybe that's enough, because I want to go on to quite a lot of other things. So anyway, let's say that I think this is promising, but it's going to be difficult. It's going to be hard. One of the hard things that's always deterred me about cryogenic things is it's very slow. It takes a long time to cool things down and warm them up. So the whole development is a slow process. But it turns out LIGO is almost as slow. To get the vacuum up and down on the LIGO things is slow too. So it may not be all that much worse. Okay, and it looks like a fundamental thing that in the end probably has to be done to get the good performance. Okay, now, So the limiting factor here, however, still is the difficulty of cooling the test masses, fighting the heat input from the beam by the light going through the transparent material. So years ago, I came up with a potential solution for that and did a lot of work and published some papers on this. And the idea I came up with was, don't put the light through the test masses at all. Instead, make the test masses, make the mirrors into diffraction gratings, and a special kind of diffraction grating. And let me show you the idea, because I think this may be a very useful idea for all kind of reasons. There was some crude tests done after I proposed the idea, discussed it with Stanford people. They made some crude, simple tests at first, but not very far into it. Now, the basic idea was, you don't want to get the light to go through the grating, but you only want to tap off a small fraction of the light. Remember, this is like a picture of the mirror from the side, and you have this very low loss reflection multi-layer dielectric mirror. So what I propose is, for example, in one version here, the most obvious one is, let's make a very low amplitude diffraction grating on perhaps just the front surface, or maybe one of the surfaces in between of this. That means let's make somehow, maybe by etching, and we found out how it can be done and so on, you etch a diffraction pattern, make a diffraction grating. You design this very carefully though. What I would be proposing was, let's illustrate it in this particular case, designed for normal incidence. If, for example, you had this mirror with a very faint, it has, let's say, an amplitude peak to peak on the front surface of about 1/10 of a wave. So it's a very small, very kind of faint diffraction grating. And so most of the mirror works just like normal. And most of the light just comes straight back in the normal way. But a little bit is coherently diffracted and will come off. If this, we've arranged, by the way, that the grating is a fine grating, not like most normal gratings. You can't use glazing. We arranged it that the width, the distance between one peak and the next peak in the grating is less than a wavelength. And we do this so that there's only one order allowed. Because a typical diffraction grating gives many orders, and you blaze the grating. You've probably come across that. That means you shape the surfaces to focus the light into a particular order. Here we don't do that. Here we pick the grating spacing so that only one order, let's say this one here, is allowed. Now there's still, so that means the shape of the grating doesn't matter very much. It could be just sinusoidal. And this would give you equal light coming off in two directions. That's a little bit of a snag, but maybe we can make use of it. Okay, and so you could easily arrange that this diffracted, say, a few % of the light, which is all you need, and that gives out, now you could run this backwards. You could feed, this could be one end of a Fabry-Perot cavity in one arm, and you'd feed in light on one of these. It would go up and down the light, and pick it out the other side, for example, and I'll show you various ways of doing that. So you could set this up so that, and no light at all is coming through here. In fact, it doesn't even have to be transparent. This is one of the big deals of this. You could do this with material that wasn't transparent, but was better for other reasons. For example, silicon is very appealing as a possible material. It's not transparent. Q is very high, can be got very pure. So that's an interesting possibility anyway, aside from this effect. So now you've completely limited absorption here. There's still a little bit of absorption in the coatings, but remember, they're only a quarter of a wavelength thick, so they're very thin. So it's going to be a big improvement. Okay, so then you can soon work through and see a whole lot of ways. How would you actually use it? Turns out, for example, this is a kind of awkwardness having two beams, so I spent a bit of time and I got a paper on various ways of using it. One way that makes it some sense simpler is to have the light coming, have an oblique incidence, and you have to think carefully about the direction. But for example, here's one in which we were coming in at an angle here, and the light is being, you get a normal, ordinary reflection at a normal angle of reflection equals angle of this, that's the main beam, but a small fraction diffracted here would come back on yourself here, and this would only give one diffracted beam coming back here, if you've picked the geometry right. So that's very interesting. Okay, so let me show you just quickly. You can play yourself and imagine all kind of ways of implementing this, which none of them have been seriously tried. I didn't have the manpower to do it, and we were doing other things, but I'll just show you some of the most obvious one, which might be usable. Oops, sorry. I've got some papers on this. I'll give you the references later if you're interested. Here's how you could make a Fabry-Perot cavity. In this case, a triangular cavity with 3 mirrors. You could use as a mote cleaner, in which you use this oblique thing you see coming in here. And it turns out you would get input coming in here. The light, it doesn't go the way you'd think. It doesn't go around this way. In fact, it goes around this way. Okay, like that. It builds up to a high intensity in here. And this here could be the output. And in fact, if you look at the equal angle here, that angle equal that angle, you'll find that this beam here is more or less cancelled out because of the phase changes. And this is where you'd put the normal reflection locking technique. You've heard of that earlier. Exactly the same old reflection locking system. You could add that, you could look at that here. So that looks like a very simple application. I wish we had time to try it. But that's certainly a simple thing for just one cavity. How do you make a 4 interferometer? I shouldn't waste time, but I'll just show you quickly. Here's a simple one, bounce interferometer. Not much practical use, but it's more to show the kind of concepts. How you could make this diffractive mirror here is acting as the beam splitter. Again, no light's going through any optics anywhere here. So you cut down losses tremendously. It's also, initially, my main reason for working on this was to think for high power, but you see, equally good for cryogenic systems. And it gets more complicated. Here's a full design for a recycling interferometer with 3 mirror cavities. You don't worry about all the details here. That one does actually use a beam splitter there, but it's carrying low power. But you can also make the same thing with no transmission anywhere. Here's a version with no transmission. It takes time to work that one out. And finally, I did show in one of the published papers I had on this, the first diagram I think I've ever seen in print suggesting a cryogenic interferometer, utilizing the idea, because this would reduce the heating. And so, in fact, here I'm suggesting just that there's a cold part here. There are baffles here to reduce heat coming in from the hot walls. I'm assuming that in this case, the pipe walls are not cold, but this cuts out the heat input into the cold part here. So this may be something like that. Was a long time ago, that paper, and it's taken a long time to get to anything like reality, but that's a possible way of doing it. Okay. So, yes, well, I got a lot of things to do. Give me a whole list of stuff. So maybe I have to stop there on that. Okay. He suggested I would talk about magnetic levitation. Well, we can run through that for fun too, if you like. It's probably not quite so significant, but we did spend some time doing experiments on it. The idea here was not quite as ambitious as making a cryogenic interferometer, which is clearly a great, big, expensive deal, but promising in the long term. Was okay, we could improve things, we could improve at least the suspension noise, which is the main one that hits you first of the thermal noises, by having no suspensions. Okay, and you just make the thing float in mid-air, or mid-vacuum. Okay, why not do that? Well, they thought, why not do it? Let's try it. We could do it with magnets, of course. Now, because we thought of lots of different magnetic arrangements, and of course it's pretty easy to levitate things with the superconductors, but as I said, you can't guarantee that you're going to get the test masses themselves to low enough temperature that they would be superconducting with ordinary superconductors. Now, maybe you could do it with high TC superconductors. You almost certainly could. The problem is, I think the expected mechanical Q of high TC superconductors isn't very good. It's not competitive with real good things like sapphire and so on. So early on decided we should try and see if we can do it all at room temperature. So the same technology would apply at any temperature. It would work at room temperature and would also work at lower temperatures. And so we started with very crude ideas, just with permanent magnets. And we played around with various geometries. And now, to make, of course, a levitated thing with permanent magnets, it's unstable by you've heard of Earnshaws theorem tells you it's unstable. You can make it stable by feedback that monitors where you are, and that's what we do here. We actually use permanent magnets to produce the fields and various conceptual designs. And we came up with one which is kind of unconventional, but we found it much easier than all the rest and probably a good one. And the idea here was, we have a specially made kind of bar magnet here that's magnetized at right angles to its length. So that's why it's different from an ordinary bar magnet. Like say North Pole on the top, South Pole on the bottom. And our test mass has, let's say, a small magnet, similar magnet, attached to it. Now, there's a snag, but we'll come back to that later. Okay. And that will obviously attract up there, and it's going to be unstable. It'll fly up and stick on there, or it'll fall down. Okay. But we monitor the height with a laser beam. And it's a simple way, we just have a beam coming along here, and if it comes up, it casts a shadow, and the photodiode sees that. We put a very small coil around this, driven by that photodiode system with amplifiers and such like, so that in fact it stabilizes itself. If you get it all right, it nicely floats at a certain height below here. The point about this geometry, compared to various others that we tried first, is this one, in principle, if this was a perfect magnet and infinitely long, there would be no change at all in the field distribution as you move in this direction. There's huge field gradients in all the other directions, and they are required to provide the lifting force on that magnet. But you arrange that the laser beam is coming in this direction, so there's no force in that direction, and so in this direction the thing is as if it's on frictionless rails. And that's exactly what you want, because that gives a very long period suspension, much longer than you get with ordinary pendulum, and just what you want. What we found in practice was the limit was set not by the length of the bar magnet, but by inhomogeneities in the magnetizations of the magnets that we had made for us. That could probably be made better. You could certainly trim it out a bit, but it was easy to get periods of the order of 10 or 20 seconds, which is exceptionally long. In fact, there's still one of these things in the lab which you can see if you like. It's a little tape, but we can set it going. If anybody's really interested, we can see it working. It's impressive to see, because you see this quite heavy thing floating there with apparently nothing holding it up, and you can go and blow it away, which is kind of, unusual. Okay, here's a diagram of one of the early versions of it. In this case, we doubled it up, 2 magnets, just so that we cancel out the effects of the Earth's field or external fields. But now already you see a hint of one of the problems. And one problem is we haven't yet found really good magnets which are high Q. And of course, if the thing has low Q, we're going to get thermal noise. So what I propose here, that we actually mount the magnets here on a little kind of standoff that isolates them, and I think that's a practical thing, but it spoils the simplicity of the idea, and not very nice. Much better if we get high-Q magnets. And maybe there are some, and we may come back to that. Anyway, so this is a kind of system like that. As soon as you get that working, what you find is, of course, with this long period, it's very sensitive to tilt. If you walk into the room and this thing is there, the thing has to come towards you. But it's not because your weight's attracting it. No, it's because you're depressing the floor, even though it's a basement solid floor. It's tilting the whole thing, and the thing is running downhill towards you, and that's why it comes towards you. So such a thing with a long period is very sensitive to tilt to the ground. So the next step is to control that, and that's what we did. And here's a more elaborate version, in which this whole lifting stage is floating between some other ones at right angles, and these are servoed by 2 laser beams here which couple together the 2 ends so that they both tilt the same amount and neither is particularly up to the ground. And this looks very promising. But at this stage we've temporarily stopped work on it because we had enough manpower, and we'd other things that seemed to be more quickly applicable to something like LIGO than this. This is a kind of rather far future idea. But here's just a picture. It's fun, this one, though, I must admit. Anybody who sees it going gets quite there. That's actually a photograph of that thing actually floating, but although you can hardly see it in the photograph as it is, but it's fun. Oh, this is a kind of dummy one. This is about it's about this size, so it's not very heavy. But that's not a problem. I mean, you could easily make it much heavier. The problem is the thermal noise in the masses. Here's an actual photograph of the 2-stage setup, in which it's pretty tricky to get it all stable, but you can. We've had it all working. Okay. Oh, yes, I had a little reminder here. Let me just say, in the course of this work at the same time, of course, I was looking for testing lots of other magnetic materials, see if we could find a high Q one. And I just mentioned, we found a very interesting material called GGG, gadolinium gallium garnet, and another version of it called the TGG, terbium gadolinium garnet. These are transparent materials, but they're also very strongly paramagnetic. Not paramagnetic, paramagnetic. So strongly paramagnetic, you can lift them up with a magnet, which is astonishing to see a thing that looks like glass, and yet you can lift it up with a magnet. Now, that's great. And the thing is, what we did, we levitated some samples of this, measured its Q. Q was fantastic. It was only a small sample because it was expensive stuff and it had to be specially made for us, but it looks very promising. The problem is that as it's paramagnetic, it has to be lifted by a field gradient, which means that it's only, paramagnetism is much weaker than ferromagnetism, although it's clearly very good in other ways. The losses looks fantastically small. It's okay to have small things you can do with quite a small permanent magnet. But once you get the LIGO size things, it requires a much bigger magnetic field because, of course, there's a gradient that will be all the way over it. So that would require a really strong magnet. And my estimates of that were you'd have to have a superconducting magnet as the lifting magnet, external, which you certainly could do, but it's getting a bit more expensive and so on and more complicated. But if you're going to make the thing cryogenic anyway, you can certainly do that. And that would be external to the main system. You can just buy these things off the shelf from Oxford Instruments, and so I had lots of discussions with them about that. Although there's a certain question, nobody quite knows how quiet a superconducting magnet really is. They don't know it at Oxford Instruments, but they think it might be quiet, quieter than you would expect in the ordinary way. So there's another conceivable I've got several more topics still, Kip. Okay, so let's skip on that one. Kip also asked me to talk about alternative topologies. Well, this is not really so exciting, but let me just mention briefly, you've heard about the standard one, the LIGO one, which is based on the Fabry-Perot concept I came up with years ago. The original proposal really to make the interferometer was from Ray Weiss, and he didn't think of Fabry-Perot's. He talked about what are called delay lines, invented by a chap called Harriot. A Harriot delay line, which is two big mirrors, and you have the beam going back and forwards on discrete spots. And that's where the German group started, where I started with coming up with a different version of that with a very small mirror at one end and called the white delay line, and then I modified it. So anyway, to cut a long story short, in the early days of this LIGO, a lot of competition between which techniques should be used. The Fabry-Perot one, Fabry-Perot won, basically because this requires much larger mirrors, because you have to have separate spots, and then you get huge mirrors, obviously very expensive, and the thermal noise almost certainly worse. You have to have a hole in the mirror, but a real killer is that a kind of unexpected problem, which in fact we discovered, and so did the German group independently in our very early tests, and the German group did too, that you have a serious problem of scattering of light from one spot to the other, because the light then can cut short a path and can come in with random phases. Bad noise source. There are tricks to improve it optically, but it's tough. So that's why right now, nobody's using delay lines. Everybody's using Fabry-Perot's or something like that, with one exception, and I'll show you that in a minute. Okay, so that's the idea. That's why people use Fabry-Perot. So it's that, but delay line, you might say, is still an alternative, and people at Stanford were proposing what they called a Sagnac interferometer, which I may stay for a little bit. Now, one interesting system is the one used by GEO. GEO is a collaboration of my German group and a group in Scotland, which I originally started before I came here, and they've collaborated together because they don't have as much money available as LIGO has, and to build an interferometer, in fact, in Germany jointly. And they're very original people there, and they came up with a totally different way of doing it, kind of different. And let me sketch it in simplified form. It's clever. It's neither a Fabry-Perot nor a delay line. The idea is this. It's in simplified form. Here's a laser, here's a beam splitter. You just send the beam once here to a test mass here, it comes back again to another test mass here, back again, and out. So it only makes 4 traverses of the beam pipe. Similarly in this arm, right? It's not multiple bounds. Comes out here. But now you throw in the idea of signal recycling and power recycling, which you've all heard about, I think. But LIGO hasn't yet been using signal recycling. The great thing is, you can realize, if you think about it, that the signal recycling lets you send the whole beam through the whole system again. So although this only has kind of 4 traverses, if you start from the very beginning with signal recycling and power recycling, which the GEO's done, then you can make up for that by your signal recycling mirror here and the power recycling mirror, send the light back again. If you do that many times, it's just equivalent to a multi-beam system. So it's an elegant idea. And in fact, it's working. That's the fantastic thing. They've thrown this together with almost no money. It's only 600 meters, and it's done on the shoestring. but it's actually working pretty well. And it's a clever idea. So there's an alternative topology which nobody talks much about, because superficially it doesn't look different, but it really is kind of different, right? I think it's very smart. The key ideas may have come from the German group, I think, which are a smart group. Anyway, it still wouldn't beat the facilities and so on. It's the same kind of problem, but it's a very ingenious idea. And it throws right at the beginning you into power scale cycling, which we all want to do anyway. So their very first one already has everything in it. Signal recycling and power recycling is an essential part of it. Not yet working well, of course. They've got all the practical problems they're trying to beat, like everybody else. But it's looking promising. Okay. Now, I did mention one other topology, which there's been a lot of talk about, but doesn't impress me all that much, which has been called the Sagnac topology, and let me say a little bit about that. This has been pushed recently by a group at Stanford, and this one, I show it here. I think Alan may have talked about it earlier, I don't know if he did here, but just in simplified form. But anyway, this is the kind of version, yeah. But you've got to watch this one, because you may not realize the problems unless you show a simplified diagram. By the way, I also published this idea as well about 83, but I didn't call it Sagnac. I had the wrong name. I just called it a resonant recycling interferometer. It was the first idea of signal recycling. The idea here is, okay, light's coming in here from a laser. You don't have a normal beam splitter. Notice that these two things which you might think of beam splitter are facing the wrong way. By the way, I saw Alan had a drawing with that wrong. They're facing the opposite way. A normal way would be facing that way, right? Okay, so anyway, some light comes, these actually are highly reflecting, 95%, so they're not normal beam splitters, okay? A little bit of light gets through this mirror, say, comes, well, I've drawn it backwards, I think, drawn the arrows backwards, it doesn't matter. Let's say it comes through here, bounces up and down the right number of times, comes back here, hits that mirror, goes right back into the other arm, bounces up in time there, comes back here, and then back here again to the first arm. So, the thing about this is that the light goes right around this path. The same light goes through both arms, one after the other. That's a smart idea. I think the first person to realize that was a German lady, Frau Schnupp, who died some years ago. She came up with this idea. Now, so the same light goes through both arms. And in fact, you might think at first sight, well, isn't the signal all going to cancel out? Well, yes, it would cancel out if you didn't have a long delay line in the arms. If there was no delay line, everything would cancel out. But if you got enough travel time to get around that loop, corresponding roughly to half a period of the gravity wave, that takes out the cancellation, and instead the two signals add up. So the nice thing about this is, well, a number of nice things about it, and nasty things too. Nice thing is that the DC, zero frequency signal, cancels out, which makes it easier to control. That's what they're kind of pushing. That's a plus. But on the other hand, you've got to have the delay lines, and they have all the same problems of delay lines, which are headaches. They need to be big mirrors, multiple scattering and bounces, and so on. So, and anyway, Stanford have been pushing this. I don't think it brings really anything new, anything reason. All the kind of calculation estimated. It's not really particularly better mathematically, but it's kind of interesting. I think I may have one more. Do I? You want me to stop, Kip? Do I have another one? No. Okay, maybe that's enough then. So that's another one. You see it mentioned, but you have to watch. Now, I proposed this, I think 83, which was the first time, but for a different purpose. Let me just tell you that. That's curious. I had it both with delay lines like this and with cavities in both arms. But this was before anybody thought of signal recycling. But this was a kind of signal recycling. The idea was, how can you detect the crab pulsar? Okay, you tune the whole thing, and that could be tuned to have very high performance, just like signal, and you can now show that it was equivalent to signal recycling. Anyway, I didn't think of the word Sagnac.
Ron, I should say I neglected to introduce Ron. I think you all know Ron, but Ron Drever came to Caltech in about 1980 to
79.
79 to initiate the gravitational wave program, and it was responsible for getting it up and going. And it's also been responsible for a large number of the.
Most of the design is really, you'll find in my early notebooks in the early 80s. You'll see my notebooks. Almost everything that's now in LIGO.
A large fraction of the key ideas.
Yeah, it's taken a long time for people to catch up and actually do it, of course, because that's the hard part.
Thank you, Ron.
Okay, thanks. I hadn't time to write references, but we can make references.
So I need to get references from you.
Yeah.
To give